Hello, welcome to the next video about IB review as we continue to go through the data book. Alright, this video goes through topic or unit C, okay, wave behavior and simple harmonic motion, which is what drives the wave behavior in the first place. Alright. Just note that this unit is quite interesting because simple harmonic motion actually have standard level, the basics, and the additional higher level formula. Okay. However, I think that if you are, once again, assuming you're watching this video from an Alberta high school, then I think that you actually learn basically most of the concept already. Most of the concept already. So in math class, so you may still find that pretty intuitive afterwards. All right, wave stuff we actually learn in additional higher level. Actually learn about Doppler effect and stuff like that. Okay, and stuff like that in the higher level, even though they are in the Alberta's curriculum. Right, Alberta curriculum. Anyhow, let's just get started and take a look at what's going on in this unit. So starting us off, this is in Physics 20. These formulas should all mostly be familiar from Physics 20. However, I'll still go through and define all the terms. All right, there are going to be overlaps here, but the key thing here is everything is going to be tied to back to something we learned earlier about forces, specifically the spring/elastic force earlier on. All right, but I do want to highlight that the simple harmonic motion definition in non-IB physics, in Physics 20 in Alberta, okay, is basically it behaves under Hooke's law, but that's not entirely accurate. Okay, entirely accurate because all springs actually behaves like under Hooke's law. And a lot of things does not behave under Hooke's law, but what really happening is the net force behaves like Hooke's law, which is more specific. So we'll take a look at the proper definition right away, and that's the first formula right here. The first one is definition of simple harmonic motion. It's any motion obeys its property. Okay, this is the definition of HHM. It says that the acceleration at any given moment is opposite and proportional to displacement. X is displacement from rest. So stretch or compression doesn't matter. Okay, but simple harmonic motion, of course, is not just for springs. It's for any kind of oscillatory motion. So this also works for really, really small angle, simple springs as well. So that's why I say displacement rest for everything I've written so far. Excuse me. So, here omega, people call W, it's actually omega, okay? All right, now, of course, definition does not require omega to be squared or anything, just some constant, okay? But it will turn out to be omega squared, okay? I'll really briefly talk about it. It's what we call angular frequency. Why do we call it angular frequency? That's because I have to draw some pictures here. Okay, I'm gonna draw a circle here. Okay, if we compare simple harmonic motion, this one I'm gonna have to draw. Simple harmonic motion. Okay, a little bit too long. To a object moving in circular motion, so that the radius is equal to the amplitude. Okay, this is maximum displacement, so write x0, amplitude is x0, radius equal to the amplitude, and they move under the same period, then the two motions is actually perfectly synced up, such that the angular acceleration, will be the same magnitude as the centripetal acceleration. Okay, and as we've seen, okay, very early on, that's triple acceleration. Okay, can be actually derived from v squared over r, and v is equal to r times w, or w equal to v over r. Very early on. Let's do a quick recap way back up here. Is it up here? No. No. Circular, right here. Okay, acceleration is equal to omega squared r. Okay, omega squared r. So we can conclude that since acceleration for circular motion is omega squared r, this one must also be omega squared while r is amplitude. So omega squared x0, negative just indicate the direction, but for circular motion that one is only the magnitude. Here we have direction as well. So both of these are actually vectors. Okay, both of these are actually vectors. All right, so once again, this came from centripetal acceleration. Don't know why the pen's not working at all now. Is equal to omega squared r. All right, it came from that by matching simple harmonic motion with circular motion. Matching simple harmonic motion and circular motion is a very, very powerful tool. That's actually where all the basic formulas come from. Okay, so while it's unlikely they will make you derive any of the formulas, it's very likely they will ask you to compare simple harmonic motion and circular motion, and if not briefly, for like one question, or discuss that, so you have an idea where all these formulas come from. So make sure you are aware of that when you're reviewing. For the exact same reason, okay, we can also get the concept of period and frequency from here. That is pretty obvious. But the last one, of course, is also, these are all stolen from circular motion. Okay, but it was not defined in a circular motion lesson earlier on. Okay, it's not defined there, but for IB, I guess the formula sort of extends backwards. So the formula is extended back there, even though period was mentioned in the formula, but not properly defined. So I guess I'll probably define it here. So wait, why is that different? What's going on? Okay, so here T is period, F is frequency. All right. So once again, there we go. So that's the formula. I put it over here. All right. So that is a simple harmonic, the basics of simple harmonic motion. Okay. Once again, these are exactly the same as for circular motion. Circular motion's angular velocity will be equal to angular period will equal to 2 pi over angular velocity as well. So this does extend from to circular. From is more accurate, okay, but since the formula sheet wise, these formulas are not on the circular motion side, so practically for us, okay, for you doing the exam, it will be more like extending to circular motion, even though that's actually where they came from. From there, by comparing circular motion, you can actually derive the period for a simple harmonic oscillator, okay, to be that. So this is the period of a simple harmonic oscillator. All right. So here M is, T is period, M is mass that's being oscillated. We're going to assume the spring or whatever is doing the oscillation itself doesn't have any mass. Okay, so the spring has no mass. The pendulum, the string has no mass, right? Okay, it's only the mass that's being oscillated, being moved. And K is the spring constant, or oscillation constant, or stiffness, whatever you want to call it. Okay, spring constant. Now, it's very important that spring constant, okay, by this definition, does not depend on the mass, but that's not the case. The spring constant can depend on other variables, including mass, and that's exactly what happens, okay, for a pendulum. Okay, for pendulum, the spring constant actually depends on the mass. So there's a factor of mass both in the numerator and in the denominator. I'm waiting for the PDF to react. Oh, it's saving. Okay, good. Because numerator and denominator both is mass, the mass actually cancels. So if you look at the second formula, which is period of a simple pendulum in small angles, okay, small angles. If you ever asked a simple harmonic motion regarding pendulum calculating, it'll always be a simple pendulum with small angles. You'll never have to deal with a complicated pendulum unless they're asking you qualitatively what's going on. I digress. Okay, still waiting for the PDF to respond here. But for pendulum, you'll notice that the formula only depends on the length and gravity. Oh, now it's taking some time. Oh, there we go. Length and gravity, which means it does not depend on the mass. So now I'm going to type it in. Period of a simple pendulum. Alright, small angle means the total angle is less than 30 degrees, which means swings about 15 degrees left, 15 degrees right. However, it's unlikely to encounter any big angles because when it becomes too big, it becomes circular motion. It becomes rotational motion, which means you have to use rigid body mechanics or rotational dynamics to actually solve properly, or at least use circular motion. Okay, at least circular motion. But small angles, you can use this formula, which is L is the length of the pendulum to center of mass, pivot, where the strings hang, to the center of mass. Okay, be careful. So if the object becomes longer, you can actually change the length. Even though the mass does not change, changing the size of the object can change the length of the string or of the pendulum. And G is gravitational field strength. If they ever change G, you'll be going to a different planet, so do not assume 9.81. Yes, most of the time we're dealing with 9.81 on Earth, but once again, if you're dealing with a pendulum question, that G is involved, most likely G changed to a different planet. Alright, so that is simple harmonic motion, the basics. Alright, there's some more, you know something's coming up, so you know what? Let's do it together. Okay, instead of jumping back and forth, let's continue. This is the higher level simple harmonic motion stuff. These actually deals with the motion itself a little bit more carefully. All right. First is the displacement. Okay, displacement or position rather. Position is more accurate. I shouldn't say displacement. First one is the displacement. Displacement is correct actually. Displacement from equilibrium. I may have to write it over here because it's a lot. Okay, all the formulas use the same thing. So x by itself is displacement from equilibrium. I define what the variables first. I'll explain what each formula means in a second. X0 is a maximum displacement from equilibrium, aka amplitude. Alright. W, you know what it is. Angular frequency. Time is time. And phi here, which looks a little funny. Looks like a circle with a line in the middle. Phi. Or as my university prof would call it, phi. Probably more correct since he is Greek, but still, we call it phi. Phi here is what we call phase shift. Okay, I'll call it initial phase because if you have the phase shift, that's where it starts. Basically, that's where the position starts. If you start at, I'll talk about it. If you start at the equilibrium, phase shift will be 0. If we start at maximum, phase shift will be pi quarters and so on. Okay. Oh, taking some time to process. phase shift. I just say phase shift. Okay, because that's a language probably used in math class. All right, and of course ET is total energy. It's EP and EK, and EP of course is potential energy. All right. So, by the way, you can, which means you can actually calculate what EK is. You can calculate what EK is. But let's take a look over here. I feel like I missed something, so I'll go back quickly. No, I'll go back to here quickly. Just over here, I remember what I missed. It's over here because acceleration is negative omega squared x. We calculate F net. Okay, F net equal to ma, of course. Will equal to negative mw squared x. All right, or if I want to write it out so it looks better, equal to negative m omega squared x. That is important. That's important because if we treat F net as spring force by Hooke's law, we can actually call this the spring constant. So that's K. So that means K equal to m omega squared, or omega squared equal to K over m. So K here is our, of course, spring constant. And that's actually what you'll need to do to drive the formula, well, this one. Because you can see, okay, you can actually see K over m over there. So period is equal to 2 pi over omega, right? And then you are done. This is important because you can see the m omega squared everywhere in the formula right here. But m omega squared is just K. It's just K. All right? I digress, but that's important. But not the most important part of this thing, but that is in the background information that you are expected to know, because once again, this is not a formula sheet, which means you are expected to be able to come up with them. All right, let's come back to the formulas we were at, all right, which is, first one is position, make it smaller, displacement, not displacement, of HHM, simple harmonic oscillator, at a given time. Alright? We're going to assume they start, because it's a sine graph, we're going to assume they start, okay, at equilibrium. So we start at equilibrium and go up and down and up and down and up and down. So that's what it's modeling. If you start at maximum, you would use a cosine. So same thing works for cosine. Okay, so you can also do cosine, but the cosine, of course, also works, but cosine, of course, start at maximum. We're going to stick with sine. If you have a phase shift, cosine would be exactly a pi half phase shift, because you shift everything to over here. All right. So basically, if your oscillation doesn't start over here, oscillation actually start like, I don't know, maybe like down here, and you start here. That's where it is. That is phi. That phase shift is phi. Let me zoom in. What's going on? There we go. So zoom in here. So if your wave didn't start, okay, let me try again. If your wave didn't start at the equilibrium, start like below here, and then it reaches equilibrium over here, and then it matches up, that difference is phi. That's why I call it a phase shift, because graphically it's just shifted. It You just shift it to the right by a little bit, right? That is what phi is. All right, that's what phi is. So hopefully that explains everything. All right, that's why it's sine, and omega, of course, is the period, 2 pi over period. Okay, 2 pi over period, which is the angular frequency, and time is time. Next one, of course, you can find by taking derivative. Okay, yes, big word, but this is basically the velocity. Of a SHM at a given time. You can find this by taking derivative of the one right above. Okay, derivative of displacement gives you velocity. If you don't know, just know the formula is that. The next one is also about the velocity, but this one's a little bit careful. This one actually uses conservation of energy to drive, or you can use trig entities if you really want to. Okay, but using conservation of energy, this is actually, notice x0 is constant, amplitude is constant, omega also, angular frequency is constant. The only variable here is actually the x. Okay, it looks like a bunch of variables, but the only variable here is actually displacement. So this is actually velocity of a small harmonic oscillator at a given position. So velocity as a function of x this time. All right. So this is actually x of t. This one is v of t, and this one is v of x. And those who like calculus, you can say, hey, wait a second, looks like I can do some chain rule here. You absolutely can, but this is not calculus class, so I will not do it. All right, there's definitely are, and a lot of things you can do with this. All right, definitely a lot of things you can do with it. All right, and last, this one is, like I mentioned, this is total energy of a simple harmonic oscillator. You'll notice when we use the modified formula calculated above, okay, the omega squared k over m, this is just 1/2 kx squared, which is pretty reasonable, right? This is just one over 2 k x0 squared, the maximum EP. Wait, no, oh, wait, not there yet, but yes, this is maximum EP. This is maximum energy in half. It's 1/2 kx squared. But you'll notice EP is equal to 1/2 kx squared. So it means this is just maximum EP, which, think about conservation of energy, it makes total sense. Right? Makes total sense. As a matter of fact, if you go by the classic way, the one on the top is derived first, and then the bottom is derived later. Okay, derived later using the other ones, but doesn't matter. Just notice that both formulas are similar. It's because both actually talking about potential energy. Okay, potential energy. So this is potential energy at given moment at a given position. Right, at a given position. But top one is maximum energy, maximum EP, so that's total energy you have as well. From here, you can calculate kinetic energy if you want. Right? You'll notice everything's consistent. Okay. Of course, this formula is on the Alberta formula sheet. Okay, Alberta formula sheet doesn't have angular frequency stuff like that. So this is what Alberta formula sheet actually records energy as spring constant. So just remember, not everything's actually a spring, so they did simplify it a little bit. Okay, but it's completely appropriate if we define spring constant as omega squared m. So that's all IB simple harmonic motion, higher level and included. Please scroll back up. There we go. Now let's continue with waves. Waves are actually much more straightforward in a sense, formula-wise, because what makes wave interesting is the conceptual half. So while I'll go over the formula still, make sure when you're studying, you're actually thinking about what wave is doing. Refraction, reflection, diffraction. Okay, diffraction has the most math here, actually. Diffraction and interference during diffraction. Once again, the formula here. Okay, but what they're actually talking about and and how the wave is supposed to be behaving. Okay, and different type of waves, longitudinal and the transversal waves, and so on and so forth. Okay. So the first one is called Snell's law. Okay. This one. All right, and ends here. I will not label what they are. Oh, I will say one is usually the initial medium, but for those for those who have learned in class, probably you'll notice that medium doesn't actually matter. So the order of the medium doesn't actually matter. It doesn't matter which one's initial, which one's final. So all that matters is there are two different mediums. The two mediums doesn't even have to be touching. It just means light travels through one medium at some point, another medium at some different point in time. Okay, so medium 1 and 2 is medium 2. Then n is the index of refraction. It's actually by definition equal to V over C. Okay. Hold on. C over V, I mean. C over V. Alright, which means you'll always be bigger than 1 because speed of light is always faster. Right, always bigger. Well, it can be equal, I guess. If travel at the speed of light, right, it'll be 1. It's greater than equal to 1. Alright. And angle is the angle of refraction in the medium. Angles are the angle of refraction in the medium. You may say, but why is it incident angle? Yes, technically incident angle would be that too. Okay, incident angle, but if the light travels backwards, the angle will be the same. So which one's incident, which one's refracted, depending on which medium is the first one. Right? Which one's the first one? So I'll just say the angle of refraction in the medium. And which one's incident, which one's actually refracted, depending on the order, okay, of you travel, but that is arbitrary. You can choose, you can go through 1 to 2, or 2 to 1, or 1 and then travel to something else, then to 2. Like, or 1 to 2, and like you can do all kind of crazy things, but the angle will always remain the same as long as it is the same medium. So I'll just say angle of refraction. Alright, and V, of course, is the speed of light in the medium. Alright, so that's the refraction formula. Next is about constructive and destructive interference. Alright, this comes together. Just note that I will draw a picture here. Cannot get away with drawing pictures. So imagine you have two sources. Alright, at some point over there. Okay, so this is source 1, source 2. You have a path from path 1. Line. Wait. From here to here. I may have to move this one. It's a little bit annoying. There we go. And another path from here to here. Alright, I'll move this one too. You have two paths. Oh, it's frozen again. You have two paths, okay? The path difference, okay, difference between the two paths is called path difference. So you have path 1, path 2. Okay, that's what we mean by path difference. So you have path 1. Path 2. So path difference is the value of L1 minus L2. Without going through details, that's what the path difference is. If a difference path is exactly an integer multiple of the wavelengths, which means the path difference is, you know, the wave arrived just exactly 1 or 2 or 3 wavelengths later, then you'll constructively interfere. If they are 1.5 or 2.5 or 3.5, which means they're about half off, then you'll destructively interfere. It's actually quite intuitive, right? So And of course, here is an integer. And some integer. Okay, some integer. So 0, 1, 2, 3. I guess it could be negative. Whatever. Right? But if I take the absolute value, there won't be any negative values. So I would just say that. Alright? And lambda is a wavelength. I haven't seen lambda for a while yet, so I'll write it down definition. Alright. The last one is the double slit. This Young's double slit formula. This is a formula Thomas Young come up. Okay. It does use small angle approximation. So this is the Young's double slit formula. Uses small angle approximation, which is doable for double slits, not so much for a diffraction grading. However, we'll get the better formula a little bit later. I'll put it over here actually. All right. Here, of course, S is distance between the maxima. Distance S is distance between the maxima. All right. Now, for Young's experiment, okay, the first few maxima he was able to observe actually are equal distance apart. Once again, that is not true when the angle gets bigger. But for the first few, okay, they are equal, so that's why I say small angle. Okay, so in particular, this is also equal to the distance from central bright spot to first order max. Right? So this is actually the x in Alberta curriculum. N equal to 1. So Alberta curriculum actually have the same formula, but the symbol they used is x. Lambda's wavelengths. Okay, d is actually distance from double slit to the screen. Double slit and slit and screen. And d is the separation of the slits. Okay, which means in Alberta curriculum, D is actually written as L. So for those who are keen and you notice this formula is actually in the Alberta formula sheet. Okay, just with different letters, that's all. Alright, so that is Young's double slit experiment. Okay, so make sure you are not confused with the one we're about to learn soon, and this only works for double slits, only a few slits. Okay, and this is what Thomas Young actually used. Okay, with that being said, let's talk about the higher level version of these. Right here. Now, if we actually want to do a general formula, okay, we have to count for a few things. Okay, first is diffraction will also occur with only one slit. I'll wait for the PDF to respond. Only one slit, and that's the first formula you see over here. This is called single slit diffraction. Because the diffraction results can be seen already in single slit. Basically, you create this really large blobs of light, okay, where the middle one's really bright. The ones on the side really faint, we barely see it, but they can be detected in a dark room. Theta is the angle to the first order minimum. Alright, first order minimum. And lambda's wavelength, that didn't change. Okay. And B in this case is width of the slit. The width of the slit basically put a hard limit on what further diffraction patterns like double slit, triple slit, or how many slits it can have on where the central maximum can be. However, what the diffraction grading is, as you get more and more, you notice each actually get narrower and narrower, and the one on each blob gets darker and darker. So eventually they become equally bright, and the envelope effect, we call it, the envelope effect actually disappears. Okay, but I digress. Oh, I spelled it's wrong. But what happened? Once again, so that's what happens when you have a diffraction. Okay, when diffraction happens. So, and then the actual general diffraction formula is one down below. Okay, this is called the general diffraction formula. All right. Oh, I should probably mention this one since I'm jumping. This is your small angle approximation as well. Actually, the more correct formula should not be using the angle, sine of the angle for big angles. Right? That's what you see over here. You see sine of the angle. Technically, it's still the long distance formula, so it's not a perfect one either. Okay, the perfect one actually gets pretty complicated. Have used tangent and stuff like that, but don't have to worry about that. Okay. The one you learn in IB is the one we're using right now. It's n lambda equal d sine theta. That, of course, is basically the notation is the same as Young's double slit one, except they don't use a small angle approximation. Instead, n is the order number. Any order could be maximum or minimum. First order, second order. Okay, first order minimum is 0.5. First order maximum is 1, and so on and so forth. All right, can be 0, 1, 2, 3. So can you even put 0.5, 1, 1.5, etc. And theta is the angle to the order fringe, max or min. N order max or min, depending on which one you're looking for. Okay. All right. So there is the general diffraction formula. All right. So that's wave properties. Okay, wave properties. And then wrapping up, it's you'll notice there is no C.4, and that C.4 is almost entirely qualitative. Okay. Let me remember, title. Okay, C.4 is standing waves and resonance. So that is actually important in setting up Bohr's model. Okay, Bohr model. But also, if you like music, okay, which hopefully there's a number of musicians here because I believe physicists make the best musicians. So if you like music, if you like sound, if you're interested in or if you don't like music and don't like sound for some strange reason, you also care about things like damping or safety regulations and metronomes, and the word is escaping me right now. Synchronization, okay, stuff like that. You can learn about that in C.4. There's no formula associated. It's just associated. It's entirely conceptual, building on top of the interference stuff you learned right above. So there's no new formulas. So that's why there's no section. The last one is Doppler effect, which is quite interesting because the IB Doppler effect is in the IB only. Doppler effect is standard level. This is the Doppler effect of light. Okay. So blue shift and red shift. Okay, red shift. Okay, so formula may at first seems like index refraction, but there's no refraction going on here. It's just a matter of things moving away and moving towards. All right. All it says here is that the change in frequency, F is a frequency, wavelengths will change by the same amount. Same ratio at least. Same proportional ratio. Same proportion. It's wavelengths. And the proportion can be determined by how fast the object's moving relative to the observer compared to speed of light. So v is the speed of the between the source and the observer. Okay, which means if you basically you have an object, let's say a distant star. Okay, a star could be rotating, right? Rotating around or orbiting something else. When it's moving away, v would be positive. Moving towards, v would be negative. You decide, okay, how you choose it, and how much frequency wavelengths change will depend on that. If it's moving towards, frequency would increase. Moving away, frequency would decrease. So I write that in too. Okay, so if towards, there's no direction in this formula, but if towards, frequency will increase. Away, frequency will decrease. Okay, frequency will decrease. And wavelengths will change by the same proportion, but in opposite amount. Wavelengths opposite. Okay, opposite. Okay, change by the same ratio. Once again, they will change by the same ratio, but in opposite direction because speed of light is constant. Frequency goes up, wavelengths goes down. All right. So that's the IB wave Doppler effect. The Doppler effect you will learn in the standard curriculum in Alberta at least. It's actually these ones, but they are higher level for some reason. But okay, these are I think they are definitely more complicated formulas, but these are actually I think more intuitive. This is Doppler effect of sound. All right, same thing. I'm not going to repeat this written, but I verbally say that frequency will increase when you move towards. Frequency will frequency will decrease when you're moving away. This one gives you more accurate calculation on just how much frequency changes. It actually tells you exactly what the frequency is because f prime is the apparent frequency. Remember, the actual frequency never actually changes. It's only apparent to have changed. Okay, appear to have changed. All right. F is a source frequency, the actual frequency if you want. All right. Now, depending on which one you're using, which reference frame you're using, okay, from whose perspective, if you have a source that's moving, okay, moving source, then you use US. That's a source speed of the source relative to the observer. You have moving source, or use UO if you have moving observer. Okay, speed of observer relative to the source. You can actually combine them because both the speed is the only thing that's moving is a medium. We always assume the medium is not moving. Okay, we assume the medium is not moving. One of the assumptions. So both are moving. You have to count for the movement for both. So you can actually combine both of them. Okay, you can actually combine both of them. Assume medium is not moving relative to whoever's doing the calculations. All right, so that's Doppler effect, and that wraps up a review for topic C. Thank you for watching.